Alright. Next section deals with the dot product. We're going to cover a minor part of this. Actually, the major part of this, but it's not that bad. It's really simple, very short section. Given two vectors, v1 is a1, a2, and v2 is a1, b1, a2, b2. The dot product is simply you take the I times the I plus the j times the j. It's an actual scalar. It's a number. It's not a vector. So if I go via the following two vectors, find the dot product. Dot product is really simple. You'll say u dot v is going to be 2, 2, dotted with 1, 1. And that is 2 times 1 plus 2 times 1. That's simply a 4. What is that used for? Well, I'm glad you're asking. Just hold your horses. You'll figure this out in a minute. And if I was given another two vectors and I wanted to find the dot product of those, again, it's fairly simple. U dot v is going to equal the I times the I, 3 times 2, plus 1 times negative 6. U dot v will equal 6 minus 6, which is a 0. And that's pretty much it. That's how you find the dot product. Now, we could use the dot product for many things. First things first. If you give me two vectors that share a common vertex, this is vector u, this is vector v. If the angle between them, and we're talking about the angle being between 0 and 180 degrees, if the angle theta is between them, then I could derive this formula for you, but that's beyond the point. I'll take cosine of theta would be u dot v, which is what we just found, divided by the magnitude of u, the magnitude of v. And that's pretty much it. So, if I take u dot v and I get it to be 0, that means the cosine of theta equals 0. And doesn't the cosine of theta equal 0 right there at 90 degrees? Doesn't that mean that those two vectors are orthogonal, which means they're perpendicular? And if you take a vector and you figure out that one vector is a multiple of the other, then that indicates that the two vectors are parallel. Or if you find theta to be 0 degrees or 180 degrees, but that's a lot of work. So, if you have a vector and a second vector running in the same direction, that's a definition of parallel. Or if you have a vector and you have another vector pointing in the opposite direction, those are also parallel. So if the angle between them is 0 degrees or 180 degrees, those would be parallel. It's easier to see if one of them is a multiple of the other. So I'm starting with the same examples, but now I'm asking a different question. Determine whether the vectors are parallel, perpendicular, or perpendicular. If the vectors are not parallel or perpendicular, find the angle between them. Do you notice if I take u, you know that v is 1, 1. If I take vector v and multiply it by 2, wouldn't that give me u? So automatically parallel. If you didn't see that, then you're going to have to use the formula. That formula is provided on your test. You don't need to memorize it. How about part B? Well, I already did this. I know they're not multiple of each other, but if I take u dot v, I already did that. That's 3 times 2 plus 1 times negative 6. That is 0. So I know this vector and this vector are orthogonal. Meaning they're perpendicular. And if I take the third vector, part, example C, if I look at that, one of them is not multiple of the other, obviously, so they're not parallel. If I take u dot v, that is 1 times 1 plus 3 times negative 2, that's negative 5. That's neither. I need to find the angle. How do you find the angle? Well, the cosine of theta equals u dot v divided by magnitude of u, magnitude of v. So u dot v I already found. I already got that to be a negative 5 over. What's the magnitude of u? Magnitude of u is the square root of 1 plus 9. That's radical 10. And what's the magnitude of v? That is the square root of 1 plus 4. That's radical 5. So what does theta equal? Well, I'll get my calculator out and I'll take the inverse cosine of a negative 5 divided by the square root of 10 times 5. It didn't put a 10. Nope, that's not enough. Here we go. Times 5. Better. I am in radian mode. 135 degrees. That's a reference angle of, so if I was to clean this up, that's negative 5 over square root of 50. Isn't that 5 radical 2? 1 over radical 2. What do you know? I just made that up and it worked out that way. Okay, there is a component of a vector on another in a projector. I'm not going to cover that this time around. Probably I'll cover it next time. But let's talk about work. Work is a very important application that we find. Normally, work is force times distance if the distance and the force line up. So if I want to move a car that much distance, and if I'm pushing, the force is matching, in which those are parallel, hopefully in the same direction, then I will simply say, take whatever the force is times the distance and everybody's happy. What if I'm pulling at an angle? What if this force is at an angle? Then some of that force is going toward the vertical component and some toward the horizontal. That means I can't move the car as far with the same force. To do that, if you could write the force as a vector and the distance as a vector, then the dot product of the two will give you work, which is extremely important for us. So I'm going to have two examples for you. Example 3. Given the force as a vector, well, that's very good. I don't need to do much work on that. The force moves an object 3 feet along the x-axis. Okay, if it moves it 3 feet along the x-axis, wouldn't you say the distance vector 3 along the x-axis in the positive, isn't that 3, 0? So how much work is done? Work, if you're able to write both of those as vector, it's simply F dotted with D. There are other ways of doing this problem, but this is how we want to do it. That is 3, negative 2, dotted with 3, 0. The force will be 9 plus 0, which is 9. What are the units? The units are pound-feet, the product of those. And that's pretty much it. Straightforward. If you could write it as a vector, that's a big deal. There are formulas you could derive. We could derive them because they really use trigonometry, but this is a much simpler way, and I want you to get used to that. A wagon is pulled horizontally by exerting a force of 30 pounds at 45 degrees. You don't need to graph it, but visualizing it make it easier. So here we are. I'm not pulling I'm pulling in this direction. If this is 30 pounds and this is 45 degrees, wouldn't you say that the force is actually the cosine of 45 times 30, which is 15 radical 2? 15 radical 2. And I want the distance. How much force is done by moving the wagon 50 feet? If I want to move the wagon 50 feet, obviously if this is where the wagon is tied and you're pulling in this direction, it's going to be pulled in that direction 50 feet. Don't you want to move it 50, 0? So the distance I could write as a vector of 50, 0. Well, isn't the work? Did I make that? Wait, I didn't make that. No, I didn't. Good. Work would be force dotted with the distance. If you could write them as a vector, that takes into account a lot of variation. Well, that is 15 radical 2. 15 radical 2 dotted with 50, 0. The work would be 50 times 15. That's 75 radical 2. You could throw that in a calculator if you wish and approximate it. But I'm just going to leave it like that, and you could even do the whole thing. Oh, 1060. What did I miss? Oh, there's 50. Right. 15 times 50 is actually not, it's 750. I missed a 0. What are the units? Pounds, feet, and there it is. Now, in your upper division courses, you're going to take that idea and you're going to modify it slightly. So make sure you grasp it this much in this section. And when we get there, we'll talk more about it. And that's pretty much it for this section.